This is a solution video for practice problems related to Newman projections. So this first question asks us to identify if the conformer is in the eclipsed or the staggered state, and then to draw the corresponding skeletal structure. So for this first one, we can see that this ethyl group and the hydrogen are on opposite sides of each other. They're not lined up, so they're not directly stacked on top of each other. And so we know that this is going to be staggered. While for this other one, we can see that the groups are kind of lined up with each other, or they're like directly over each other. And so this one's going to be eclipsed. And so to convert these to the skeletal structure, we'll start off with that first middle bond. So this is going to be that carbon front and carbon back. And so I'll label that as CF and CB. And we'll end up having the same thing for this eclipsed one on the bottom too. And then from here, we want to draw in first the in-plane groups. And so since we're in the staggered states, our groups are going to be on the opposite side of that middle carbon bond. And then the ethyl group on the left carbon is going to be pointed up. And so we can draw in a ethyl group right here. And then this hydrogen is going to be in plane, pointed down. And so here we can see that these are on opposite sides of that carbon bond, indicating that it's in the staggered state. All right, from here, we have to fill in the dashed and the wedged groups. So the ones on the right side are going to be wedged to show that they're projecting forward. So that methyl group is on that front carbon. And then the other methyl group is in the back. And we also want these on the opposite sides of that middle carbon-carbon bond. Next, we want to draw in the chlorines. And so these are both going to be dashed. Because they're on the left side of the molecule. And we have one on the front carbon, one on the back. All right, so that's it for that first one. You can also omit that hydrogen since skeletal structures imply their presence. So either you don't necessarily have to draw this hydrogen. All right, next we can do the other one. And so we can add in the eyes for both of these to show which direction we're looking at. And so for this first one, we first want to draw in the hydrogen and the bromine. And so these are both pointed up and they're eclipsed. And so in the structure, we're going to draw them both pointing up and on the same side of that carbon-carbon bond. Next, we're going to add in the other groups. So we have on the front carbon, we have an isopropyl group and a methyl group. The isopropyl and the hydrogen are going to be wedged. So we can do ipro here and an H on that back carbon. And then the groups that will be dashed will be that ethyl and the methyl groups. And so that's the structure that we should get here. All right, for this next question, we want to draw the skeletal structure of the conformer that corresponds to the lowest energy state. And so before we convert this to a skeletal structure, we first want to rotate this Newman projection so that we're in the lowest energy state. And so for the lowest energy state, we want to take our biggest groups. So in this case, this T-butyl is the biggest group that we have. And we want to make sure that it's surrounded by the smallest groups. And so the smallest groups on the back carbon are going to be these two hydrogens. And so we want to rotate that back carbon until those hydrogens are on opposite sides of that T-butyl group. And so first I'm going to redraw that front carbon. I'm going to keep it exactly the same. And next we're just rotating that back carbon. So we're going to go that way. And we also want the staggered state, so we don't want the groups lined up. We want them to be kind of spread out throughout the circle. And so this should be our lowest energy state conformer. Next, we can convert this to a skeletal structure. So for this, similar to the previous question, we'll draw in that middle carbon-carbon bond. Next, we're going to take the T-butyl and the ethyl group and draw them out opposite sides of each other. And we want that T-butyl group pointed up because it's up in that Newman projection. Next, we will take the groups on the right. These two are going to be wedged. So the chlorine's on that front carbon, and that hydrogen is on the back carbon. And then we will have the other hydrogens will be dashed. All right. Okay, all right, so this next one is just converting some skeletal structures to their Newman projections. If you haven't done so already, I recommend going through that video of steps to drawing a Newman projection. We'll be following these steps as we go through and solve these. So for this first one, our first step is to identify the front and the back carbons. So I'll draw red dots that correspond to the front and the back. Next, we want to fill in the hydrogens. So right now, both of those carbons are missing 2 hydrogens. So I'll draw those in here. And we want to identify the 3 groups that are on each carbon. So those blue ones are on that front carbon. And the 2 hydrogens and the methyl group are on that back carbon. Next, we want to take our in-plane atoms. So I'll highlight these in red. So these red ones are those in-plane atoms. And identify if it's in the staggered or the eclipsed conformation. And so here we can see that that methyl group and the chlorine are on opposite sides. We can see that they're on opposite sides of that middle carbon-carbon bond. So for this, we would want to use the staggered state since they're on opposite. And then we also want that chlorine on the front carbon pointing down. So to draw our correct empty Newman projection, we would place that front group pointed down, and then the back carbon would be staggered. Next, we fill in the 2 groups that are red, so that chlorine is pointed down, and then that methyl group is pointed up. And then finally, our last step is to fill in all the hydrogens. We just have hydrogens here, so I'll just put those in here. And just to remind ourselves, those blue ones are on that front carbon, and those green ones are on the back. All right, so that's the first one. Let's do this next one. So same thing, we're going to draw a red line through the in-plane groups. And before I forget, I'm going to fill in those hydrogens that are here. So we have a wedged one on that front carbon and a dashed one on that back carbon. Next, we can draw in our empty Newman projection circle. And here we can see that those 2 red in-plane groups are facing the same direction. They're both pointed up. And so based off that, we know that it's going to be in the eclipse state with the 2 groups pointing up. And so our empty Newman projection is going to look something like this, where our top line is going up, and then in the back carbon, they're all kind of lined up or eclipsing the front carbon. Next, we can fill in those first groups in plane. So that's going to be the chlorine on that front carbon, and then an ethyl group on that back carbon. And then next, we have that the wedged groups are going to be on the right side of the molecule. So this hydrogen is on the front carbon, then a methyl is on that back carbon. And then the dash groups are going to be the isopropyl group on that front carbon, and then a hydrogen in the back. And similar to that first one, I'm going to highlight that front carbon in blue to kind of show how all of those are coming together towards that front carbon. All right. Next, let's do this last one here. So similar as before, let's start off with filling in our hydrogens. So we should have a dashed hydrogen on this back or carbon here, and then a wedged one on this front carbon. Next, we'll take our in-plane groups. so the ones that are not dashed and not wedged. And we can see that they're on opposite sides, so it's kind of like a zigzag. And we can also see that the fluorine is facing up. And so our empty Newman projection should look like this, where we have this fluorine coming up. And then we have that back carbon is going to be staggered. And we know it's staggered because those two groups are on opposite sides of that middle carbon-carbon bond. Next, we fill in the in-plane group. So we have that fluorine, we already filled that in, and then we have the ethyl group pointing down. Next, we have that the wedged groups here, this hydrogen and the chlorine, are going to be on the right side of the molecule. So that hydrogen will be here, and that chlorine will be here. And then we have the dash groups, so that bromine is on that front carbon, and the hydrogen is on that back carbon. All right. Okay. All right, so this next one is going to, given a skeletal structure, we want to draw the highest energy state and the lowest energy state. And so let's start off by first drawing the Newman projection of the given structure. So this is going to be the given, and then we'll rotate it to give us the highest and the lowest energy. So here, let's start off with that empty circle, and then also fill in those hydrogens that are missing. And then here we can see that the wedge groups are on the same side of the line, which means that the hydrogen that's missing is in plane and pointed up, because the in plane groups are always on the opposite side of the dashed and the wedge. And so what that means is that we're given a structure in its eclipse state because we have those bromine and the hydrogen are on the same side of that carbon bond. And so our first Newman projection, or the one that we're given, should be in the eclipse state, where that bromine and the hydrogen are pointed up. Next, we want to fill in the other group, so that front carbon just has two hydrogens. And then finally, for the back carbon, that chlorine is on the right and the dashed group is on the left. And so this is our first structure. And so we can see that we're in a eclipse state, which means that we are in a high energy conformation already. However, we're not in the highest possible one because right now our bromine and our hydrogen are lined up, and our hydrogen and our chlorine are lined up. And the worst possible eclipse, or the two biggest groups that we have, are chlorine and bromine. And so the highest energy state would end up having those chlorine and the bromines eclipse. And so to get that, we're going to keep that front carbon the same. So we'll have our bromine pointed up, those two hydrogens to the side. And then next, we would want to place this chlorine facing up, and then rotate all the other groups that same amount. So basically, they're all going 120 degrees here. And so those two hydrogens will end up aligning with the other hydrogens. And so this would be our highest energy conformation here. To get the lowest energy, we would want to do the opposite. So we would want to have that chlorine and the bromine be opposite sides from each other. And so again, we're going to keep that front carbon the same. We have bromine, hydrogen, hydrogen. And then we're going to want a staggered conformation where that chlorine is placed as far away as possible from the bromine and are on opposite sides. And so these should be the final structures that we get. And again, whenever you're asked to draw the highest energy or the lowest energy conformers, you always want to keep in mind that the highest energy conformer is the one that's eclipsed, and the lowest energy one is the one that's staggered with the biggest group that's opposite each other. All right, so for this next one, we're supposed to fill in the energy diagram for the given compound. And so here we're given the structure where the methyl group and the OH are opposite each other at 0 degrees. And so this is going to be our lowest energy state because those biggest groups are opposite each other. And so based off of these structures, we should also double check that our energy. So in this structure, we don't have any eclipsed conformations, and then that methyl and OH are not gauche to each other. They're currently opposite sides. So we can assume that this energy state is at 0. And so we'll put a purple dot right here to represent 0 energy at, or minimal energy at 0. Next, we want to start rotating. And so for this, the way that I'm going to do this is keep the front carbon the same, but I'm going to rotate that back carbon. So I'll just copy that over. And once we rotate 60 degrees, we should end up in a eclipsed conformation. So before I rotate all these, I'm just going to copy over each one for, just so I have an empty one for each of the conformations. All right, so for this one, we rotated 60 degrees. Let's rotate clockwise. So we're taking these back ones and rotating them all 60 degrees. So we should end up with the hydrogen and the methyl here overlap, these two hydrogens, and then this OH. And so that's our representation for 60 degrees. And so now we have to calculate the energies that correspond to that state based off of that table. And so here we can see that we have several groups eclipsing. We have this methyl and this hydrogen. And so based off of the chart, we can see that that's +5. Then we have a hydrogen and hydrogen eclipsing, so that's +4. And then we have a hydrogen and an OH group eclipsing, so +5. And so we have a total of +14 here. And so our energy at 60 should go up to 14. And so we'll put a dot right here. Next, we can rotate another 60 degrees, and now we're back to a staggered conformation with everything just moved over, a total of 120 degrees in the back. And from here, we can calculate the energies that we have. So we have a gauche, methyl, and OH group. And so that's +4. And then that's the only gauche interactions that we have that have a corresponding energy. And so this state will be +4. So if we go back to our chart, we can do an approximate +4 here and draw the energy down to that. Next, we keep going, rotated another 60 degrees. Now that OH, now we're back to an eclipse state. And what we can see here is now that that OH and methyl group are actually completely eclipsed here. And so now we have a +15 from that, and then a +4 from each of the two hydrogen interactions. So we have a total of +23. And so we can draw this energy right here. And we can predict that this is going to be the highest energy conformer because we have the two biggest groups that are overlapping with each other in the eclipse state. Right. Next, we can rotate another. And I'm not going to talk through exactly what how I'm rotating here, but basically we just keep on rotating that 60 degrees. We similarly to before are back to that +4 energy because we have a methyl and an OH that are gauche. And so we're back down to +4 here. Next state, we're going to be eclipsed again. So now we have the OH here. And we can calculate the different energies. So a methyl and a hydrogen eclipse would be +5. An OH and an H eclipse would be +5 also. And then we have a +4 from that hydrogen-hydrogen eclipse state. And so we're back to +14 here. And then for this last state, the 360 is a full rotation around. So we're just back to that one that we started with, which is at 0. So 0 and 360 should always line up. It's a good way to double check that you also did all the rotations correctly, because after you rotate that last 160 degrees, you should be back to the exact same structure that you started. So this structure should match this one. And so that one's back to 0 because we don't have any string between the groups. All right. And so if we were to label our highest energy conformer, that would be that +23. And then our lowest energy would be that 361. And then everything in the middle would be intermediate. And the main thing to point out with those is that we're alternating between those eclipsed and staggered states, where the staggered states are always lower than in the eclipsed states. All right, and that wraps up these practice problems.